worldwideweb.++.com/doc/tutorials/pointers/ Learning C++ by listening, Part 12: Pointers. A learn by listening exercise. In earlier chapters, variables have been explained as named locations in the computer's memory which can be accessed by their identifier, open parenthesis, their name, close parenthesis, each of which stores a single unit of data of some specific type. This way, the program does not need to care about the physical address of the data in memory, semicolon. It simply uses the identifier whenever it needs to refer to the variable. For a C++ program, the memory of a computer is like a succession of memory cells, each 1 byte in size, and each with a unique address. These single byte memory cells are ordered in a way that allows data representations larger than 1 byte to occupy memory cells that have consecutive addresses. This way, each cell can be easily located in the memory by means of its unique address. For example, the memory cell with the address 1776 always follows immediately after the cell with address 1775 and precedes the one with 1777, and is exactly 1000 cells after 776 and exactly 1000 cells before 2776. When a variable is declared, the memory needed to store its value is assigned a specific location in memory, open parenthesis, its memory address, close parenthesis. Generally, C++ programs do not actively decide the exact memory addresses where its variables are stored. Fortunately, that task is left to the environment where the program is run. Generally, an operating system that decides the particular memory locations on runtime. However, it may be useful for a program to be able to obtain the address of a variable during runtime in order to access data cells that are at a certain position relative to it. The address of operator, open parenthesis, ampersand, close parenthesis. The address of a variable can be obtained by preceding its name with an ampersand sign, known as the address of operator. For example, foo equals ampersand, myvar, semicolon. This would assign the address of variable myvar to foo, semicolon, by preceding the name of the variable myvar with the address of operator, open parenthesis, ampersand, close parenthesis, We are no longer assigning the content of the variable itself to foo, but its address. When running within a modern operating system, the actual address of a variable in memory cannot generally be known before runtime, but let's assume, in order to help clarify some concepts, that myvar is placed during runtime in the memory address 1776. In this case, consider the following 3-line code fragment: line 01 of 03, myvar equals 25, semicolon. Line 02 of 03, foo equals ampersand, myvar, semicolon. Line 03 of 03, bar equals myvar, semicolon. After executing that code, the value of the 3 named variables are: 1 of 3 myvar is 25. 2 of 3 foo is 1776. 3 of 3 bar is 25. First, we have assigned the value 25 to myvar, open parenthesis, a variable whose address in memory we assumed to be 1776, close parenthesis. The second statement assigns foo, the address of myvar, which we have assumed to be 1776. Finally, the third statement, assigns the value contained in myvar to bar. This is a standard assignment operation, as already done many times in earlier chapters. The main difference between the second and third statements is the appearance of the address of operator, open parenthesis, ampersand, close parenthesis. The variable that stores the address of another variable, open parenthesis, like foo, in the previous example, close parenthesis, is what in C++ is called a pointer. Pointers are a very powerful feature of the language that has many uses in lower-level programming. A bit later, we will see how to declare and use pointers. Dereference operator, open parenthesis, asterisk, close parenthesis. As just seen, a variable which stores the address of another variable is called a pointer. Pointers are said to point to the associated variable in memory, because they store the address of the beginning of the associated, named, memory cells, no matter how many adjacent bytes are required to hold the entire variable, string, or larger, name structure. In both C and C++, an interesting property of pointers is that they can be used to access the associated variable easily. This is done by preceding the pointer name with this special operator known as the double quote, dereference operator double quote, comma, represented by an asterisk, open parenthesis, asterisk, close parenthesis. The operator itself can be read as double quote, value pointed to by double quote. Accordingly, the dereference operator is the opposite of the address dash of operator. Therefore, comma, following with the values of the previous example, comma, the following statement colon. As equals asterisk, foo, semicolon. This could be read as colon double quote, as gets the value pointed to by foo, double quote, comma, and the statement would actually assign the value 25 to as, comma, since foo is 1776, comma, and the value pointed to by 1776, open parenthesis, following the example above, close parenthesis, would be 25. It is important to clearly differentiate that foo refers to the value 1776, while asterisk foo, open parenthesis, with an asterisk preceding the identifier, close parenthesis, refers to the value stored at address 1776, which in this case is 25. Notice the difference of including or not including the dereference operator. Consider the following to dash line code segment, open parenthesis. I have added an explanatory comment of how each of these two expressions could be read, close parenthesis, colon. Line 01 of 02 as equals foo, semicolon, slash as gets the value of foo, open parenthesis, previously set to 1776, close parenthesis. Line 02 of 02 as equals asterisk, foo, semicolon, slash as gets the value pointed to by foo, open parenthesis, previously set to 25, close parenthesis. The reference and dereference operators are thus complementary. Ampersand is the address dash of operator, and can be read simply as double quote, address of double quote. Asterisk is the dereference operator, and can be read as double quote, value pointed to by double quote. Thus, they have sort of opposite meanings. An address obtained with ampersand can be dereferenced with asterisk. Earlier, we performed the following two assignment operations: 01 of 02 my r equals 25, semicolon, 02 of 02 foo equals ampersand my r, semicolon. Right after these two statements, all four of the following expressions would give true, as result: 01 of 04 my r equals 25. 02 of 04 ampersand my r equals 1776. 03 of 04 foo equals 1776. 04 of 04 asterisk foo equals 25. The first expression is quite clear, considering that the assignment operation performed on my r was my r equals 25. The second one uses the address dash of operator, open parenthesis, ampersand, close parenthesis, which returns the address of my r, which we assumed to have a value of 1776. The third one is somewhat obvious, since the second expression was true and the assignment operation performed on foo was foo equals ampersand, myver. The fourth expression uses the dereference operator, open parenthesis, asterisk, close parenthesis, that can be read as double quote, value pointed to by double quote, and the value pointed to by foo is indeed 25. So, after all that, you may also infer that, for as long as the address pointed by foo remains unchanged, the following expression will also be true: asterisk, foo equals myver. Declaring pointers. Experience has shown that it is handy to use pointers in mathematical expressions in order to calculate the addresses of adjacent items in memory, and the double quote, C double quote, and double quote, C++ double quote languages include built dash in mathematical tools to automate these calculations. This means that the compiler always needs to know the size of the variable, string, array, or larger structure associated with the name of each pointer. Accordingly, the declaration of a pointer needs to include the data type for which the new pointer will contain a memory address. The declaration of pointers follows this syntax: type asterisk, name, semicolon. Where type is the data type pointed to by the pointer. This type is not the type of the pointer itself, but the type of the data the pointer points to. For example, consider these three lines: Line 01 of 03 int asterisk number, semicolon. Line 02 of 03 char asterisk character, semicolon. Line 03 of 03 double asterisk decimals, semicolon. These are three declarations of pointers. Each one is intended to point to a different data type, but, in fact, all of them are pointers, and each of the three pointers is likely going to occupy the same amount of space in memory. Open parenthesis. The size in memory of a pointer depends on the platform where the program runs. Close parenthesis. Nevertheless, the data to which they point to do not occupy the same amount of space, nor are of the same type. The first one points to an int, the second one to a char, and the last one to a double dash, precision floating dash, point number. Therefore, although these three example variables are all pointers, they actually have different types, int asterisk, char asterisk, and double asterisk, respectively, depending on the data type to which they point. Here is a confusing part of the double quote, C double quote, and double quote, C++ double quote, languages that can be challenging for beginners, The asterisk is found in interrelated but different contexts within your source code. In these last examples, the asterisks were used when declaring a new pointer, and they mean that each is to be interpreted by the compiler as a new pointer. Open parenthesis. In this context, it is part of its type specifier, used to describe the specifics of a new pointer. Close parenthesis. This should not be confused with the double quote, dereference operator double quote, seen a bit earlier, but which is also written with an asterisk. Open parenthesis. Asterisk. Close parenthesis. They are simply two different things represented with the same sign. Let's see a 17-line example on pointers, which creates two new integer variables named double quote, first value double quote, and double quote, second value double quote, respectively, without initializing them. Then, an integer pointer named double quote, my pointer double quote, is created without initializing it. After that, a new pointer is used to store values into and subsequently display new values for each of the two previously initialized new integer variables. Here's the code: line 01 of 17 / my first pointer. Line 02 of 17, $, include left angle bracket, iostream right angle bracket. Line 03 of 17, using namespace std, semicolon. Line 04 of 17. Line 05 of 17, int main, open parenthesis, close parenthesis. Line 06 of 17, open curly brace. Line 07 of 17, int first value, second value, semicolon. Line 08 of 17, int asterisk, my pointer, semicolon. Line 09 of 17. Line 10 of 17, my pointer equals ampersand, first value, semicolon. Line 11 of 17, asterisk, my pointer equals 10, semicolon. Line 12 of 17, my pointer equals ampersand, second value, semicolon. Line 13 of 17, asterisk, my pointer equals 20, semicolon. Line 14 of 17, cout, double left arrow, double quote, first value is double quote, double left arrow, first value, double left arrow, single quote, new line, single quote, semicolon. Line 15 of 17, cout, double left arrow, double quote, second value is double quote, double left arrow, second value, double left arrow, single quote, new line, single quote, semicolon. Line 16 of 17, return 0, semicolon. Line 17 of 17, close curly brace. When that code was executed, it generated the following output: first value is 10s, second value is 20. Notice that even though neither first value nor second value are directly set any value in the program, both end up with a value set indirectly through the use of my pointer. This is how it happens: first, my pointer is assigned the address of first value using the address dash of operator, open parenthesis, ampersand, close parenthesis. Then, the value pointed to by my pointer is assigned a value of 10. Because, at this moment, my pointer is pointing to the memory location of first value, this in fact modifies the value of the integer stored at the memory whose location is associated by the compiler with the name double quote, first value double quote. In order to demonstrate that a pointer may point to different variables during its lifetime in a program, the example repeats the process with second value and that same pointer, my pointer. Here is a 20-line example, a little bit more elaborated: Line 0, 1 of 20, / more pointers. Line 0, 2 of 20, pound sign, include left angle bracket, IOStream right angle bracket. Line 0, 3 of 20, using namespace STD semicolon. Line 0, 4 of 20. Line 0, 5 of 20, int main, open parenthesis, close parenthesis. Line 0, 6 of 20, open curly brace. Line 0, 7 of 20, int first value equals 5, second value equals 15, semicolon. Line 0, 8 of 20, int asterisk, P1, asterisk, P2, semicolon. Line 0, 9 of 20. Line 10 of 20, P1 equals ampersand, first value, semicolon, / P1 equals address of first value. Line 11 of 20, P2 equals ampersand, second value, semicolon, / P2 equals address of second value. Line 12 of 20, asterisk, P1 equals 10, semicolon, / value pointed to by P1 equals 10. Line 13 of 20, asterisk, P2 equals asterisk, P1, semicolon, / value pointed to by P2 equals value pointed by P1. Line 14 of 20, P1 equals P2, semicolon, / P1 equals P2, open parenthesis, value of pointer is copied, close parenthesis. Line 15 of 20, asterisk, P1 equals 20, semicolon, / value pointed by P1 equals 20. Line 16 of 20. Line 17 of 20, see out, double left arrow, double quote, first value is double quote, double left arrow, first value, double left arrow, single quote, new line, single quote, semicolon. Line 18 of 20, see out, double left arrow, double quote, second value is double quote, double left arrow, second value, double left arrow, single quote, new line, single quote, semicolon. Line 19 of 20, return 0, semicolon. Line 20 of 20, close curly brace. When that code is executed, the following output is displayed : first value is 10s, second value is 20. Each assignment operation includes a comment on how each line could be read : that is, replacing ampersands by double quote, address of double quote, and asterisks by double quote, value pointed to by double quote. Notice that there are expressions with pointers P1 and P2, both with and without the dereference operator, open parenthesis, asterisk, close parenthesis. The meaning of an expression using the dereference operator, open parenthesis, asterisk, close parenthesis, is very different from one that does not. When this operator precedes the pointer name, the expression refers to the value being pointed, while when a pointer name appears without this operator, it refers to the value of the pointer itself. Open parenthesis, that is, the address of what the pointer is pointing to, close parenthesis. Another thing that may attract your attention is the line : int asterisk, P1, asterisk, P2, semicolon. This declares the two pointers used in the previous example. But notice that there is an asterisk, open parenthesis, asterisk, close parenthesis, for each pointer, in order for both to have type and asterisk, open parenthesis, pointer to int, close parenthesis. This is required due to the precedence rules. Note that, if instead the code was : int asterisk, P1, P2, semicolon. P1 would indeed be of type and asterisk, but P2 would be of type int. Spaces do not matter at all for this purpose. But anyway, simply remembering to put one asterisk per pointer is enough for most pointer users interested in declaring multiple pointers per statement. Or even better, use a different statement for each variable. Pointers and arrays. The concept of arrays is related to that of pointers. In fact, arrays in double quote, C double quote, and in double quote, C plus double quote, work very much like pointers to their first elements, and actually, any such array can always be implicitly converted to a pointer of the proper type. For example, consider these two declarations: line 0, 1 of 0, 2, int my array left square bracket 20 right square bracket, semicolon. Line 0, 2 of 0, 2, int asterisk, my pointer, semicolon. The following assignment operation would be valid: my pointer equals my array, semicolon. After that, my pointer and my array would be equivalent and would have very similar properties. The main difference being that my pointer can be assigned a different address, whereas my array can never be assigned anything, and will always represent the same block of 20 elements of type int. Therefore, the following assignment would not be valid: my array equals my pointer, semicolon. Let's see a 17 dash line example that mixes arrays and pointers colon. Line 0, 1 of 17 / more pointers. Line 0, 2 of 17, pound sign, include left angle bracket, IOStream right angle bracket. Line 0, 3 of 17, using namespace std semicolon. Line 0, 4 of 17. Line 0, 5 of 17, int main, open parenthesis, close parenthesis. Line 0, 6 of 17, open curly brace. Line 0, 7 of 17, int numbers left square bracket 5 right square bracket, semicolon. Line 0, 8 of 17, int asterisk, b, semicolon. Line 0, 9 of 17, b equals numbers, semicolon, asterisk, b equals 10, semicolon. Line 10 of 17, b plus plus, semicolon, asterisk, b equals 20, semicolon. Line 11 of 17, b equals ampersand, numbers left square bracket to right square bracket, semicolon, asterisk, b equals 30, semicolon. Line 12 of 17, b equals numbers plus 3, semicolon, asterisk, b equals 40, semicolon. Line 13 of 17, b equals numbers, semicolon, asterisk, open parenthesis, b plus 4, close parenthesis, equals 50, semicolon. Line 14 of 17, 4, open parenthesis, in n equals 0, semicolon, and left angle bracket, 5, semicolon, and plus plus, close parenthesis. Line 15 of 17, see out, double left arrow, numbers left square bracket and right square bracket, double left arrow, double quote, comma, double quote, semicolon. Line 16 of 17, return 0, semicolon. Line 17 of 17, close curly brace. When this code was executed, comma, the following output was generated, comma, proving that all 5 members of the integer array that we named double quote, numbers double quote, were assigned to dash, digit values according to a pattern that increments tenfold at each step. All of those assignments were made through the same pointer named double quote, p double quote, which was declared to be a pointer to an integer when it was created, comma, using the hard dash, coded values double quote, 10, 20, 30, 40, 50 double quote. Here is that output colon. 10, 20, 30, 40, 50, Pointers and arrays support the same set of operations, comma, with the same meaning for both. The main difference being that pointers can be assigned new addresses, comma, while arrays cannot, comma, because each C or C++ double quote, array double quote, is permanently assigned to the address of the section of memory to which the compiler has given a specific name. In the chapter about arrays, comma, brackets, open parenthesis, left square bracket, right square bracket, close parenthesis, were explained as specifying the index of an element of the array. Well, comma, in fact these brackets are a dereferencing operator known as an double quote, offset operator double quote. They dereference the variable they follow just as asterisk does, comma, but the syntax through which they are described also adds a number between brackets to specify the offset within the array to the specific array element that is being dereferenced. For example, comma, consider these 2 lines, comma, in which a previously declared variable named double quote, x double quote, could have been either an array or a pointer colon. Line 0, 1 of 0, 2, x left square bracket 5 right square bracket equals 0, semicolon. Line 0, 2 of 0, 2, asterisk, open parenthesis, x plus 5, close parenthesis, equals 0, semicolon. These 2 expressions are equivalent and valid, comma, not only if x is a pointer to some type of data, comma, but also if x is an array of data of that type. Remember that the name of any array can be used just like a pointer to its first element. Pointer initialization. Pointers can be initialized to point to specific locations at the very moment they are defined. Consider these 2 lines, comma, which declare a new integer variable named double quote, my r double quote, and a new pointer to an integer named double quote, my ptr double quote, comma, initializing it with the address of my r so that it double quote, points double quote, at my r colon. Line 0, 1 of 0, 2, int my r, semicolon. Line 0, 2 of 0, 2, int asterisk, my ptr equals ampersand, my r, semicolon. The resulting state of variables after that code is the same as after these 3 lines, colon. Line 0, 1 of 0, 3, int my r, semicolon. Line 0, 2 of 0, 3, int asterisk, my ptr, semicolon. Line 0, 3 of 0, 3, my ptr equals ampersand, my r, semicolon. Take a closer look at line 03 of 03 above. Here it is again colon. Line 03 of 03, my PTR equals ampersand, my R, semicolon. Notice that no asterisk is used in line 03 when the address of double quote, my R double quote, is copied into double quote, my PTR double quote. That is, because my PTR had already been declared in the line above. Once pointers are declared, the compiler knows that they will always be used to hold an address. Accordingly, it would be unnecessary and incorrect if that third line included meta-referencing asterisk like this colon. Line 03 of 03 asterisk, my PTR equals ampersand, my R, semicolon. Take another look at line 02 of 03 above. Here it is again colon. Line 02 of 03 in asterisk, my PTR, semicolon. The asterisk in the pointer declaration at line 2 only indicates that it is a pointer. It is not the dereference operator. Both things just happen to use the same sign colon asterisk. Because pointers always contain an address, pointers can be initialized either to the address of a variable, open parenthesis, such as in the case above, close parenthesis, or to the value of another pointer, open parenthesis, or array, close parenthesis, as shown in these three lines, which declare a new integer variable named double quote, my R double quote, and two new pointers to integers named double quote, foo, double quote, and double quote, R double quote, colon. Line 01 of 03 int my R, semicolon. Line 02 of 03 int asterisk, foo, equals ampersand, my R, semicolon. Line 03 of 03 int asterisk, R equals foo, semicolon. Notice the two asterisks in each of the lines declaring pointers. Those lines may look like line 03 from the previous example, open parenthesis, where we emphasized that an asterisk was not needed, close parenthesis, but the situation is different here, because in this case, these new variables double quote, foo, double quote, and double quote, R double quote, have not been declared before. The asterisk tells the compiler that these are pointers to integers, which gives the compiler enough information to correctly interpret their subsequent initializations. As you might deduce from studying those lines, after they are executed, both of the integer pointers double quote, foo, double quote, and double quote, R double quote, point at double quote, my R double quote, even though they were each initialized using different techniques. In the last case, the compiler already knows that double quote, foo, double quote, contains an address, so when it is copied into double quote, R double quote, there is no need to include the ampersand. Pointer arithmetics. To conduct arithmetical operations on pointers is a little different than to conduct them on regular integer types. To begin with, only addition and subtraction operations are allowed, semicolon. The others make no sense in the world of pointers. But both addition and subtraction have a slightly different behavior with pointers, according to the size of the data type to which they point. When fundamental data types were introduced, we saw that types have different sizes. For example, char always has a size of 1 byte, short is generally larger than that, and int and long are even larger, semicolon, the exact size of these being dependent on the system. For example, let's imagine that in a given system, char takes 1 byte, short takes 2 bytes, and long takes 4. Suppose now that we define 3 pointers in this compiler with these 3 lines, Line 01 of 03 char asterisk, my char, semicolon. Line 02 of 03 short asterisk, my short, semicolon. Line 03 of 03 long asterisk, my long, semicolon. And that we know that they point to the memory locations 1000, 2000, and 3000, respectively. Therefore, if we write these 3 lines, Line 01 of 03 plus MYCHAR semicolon. Line 02 of 03 plus MYSHORT semicolon. Line 03 of 03 plus MYLONG semicolon. My char, as one would expect, would contain the value 1001. But not so obviously, my short would contain the value 2000 and my long would contain 3004, even though they have each been incremented only once. The reason is that, when adding 1 to a pointer, the pointer is made to point to the following element of the same type, and therefore, the size in bytes of the associated data type is added to the pointer. This is applicable both when adding and subtracting any number to a pointer. It would happen exactly the same if we wrote these three lines colon. Line 0, 1 of 0, 3, my char equals my char plus 1, semicolon. Line 0, 2 of 0, 3, my short equals my short plus 1, semicolon. Line 0, 3 of 0, 3, my long equals my long plus 1, semicolon. Regarding the increment, open parenthesis plus plus close parenthesis, and decrement, open parenthesis, dash, dash, close parenthesis, operators, comma, they both can be used as either prefix or suffix of an expression, comma, with a slight difference in behavior, colon. As a prefix, comma, the increment happens before the expression is evaluated, comma, and as a suffix, comma, the increment happens after the expression is evaluated. This also applies to expressions incrementing and decrementing pointers, comma, which can become part of more complicated expressions that also include dereference operators, open parenthesis, asterisk, close parenthesis. Therefore, comma, consider the following single-line expression, colon. Line 0, 1 of 0, 1, asterisk, b plus plus, semicolon. In English, comma, we might read that as double quote, get the value indicated by the pointer named b and then post dash, increment b, double quote. As we might expect, comma, we would get a different result if that line had been written to pre-dash, increment b like this, colon. Line 0, 1 of 0, 1, asterisk plus plus b, semicolon. In English, comma, we might read that as double quote, increment the pointer b and then get the value to which it points, double quote. Essentially, comma, these are the four possible combinations of the dereference operator with both the prefix and suffix versions of the increment operator, open parenthesis, the same being applicable also to the decrement operator, close parenthesis, they are colon. 0, 1 of 0, 4, asterisk, b plus plus, semicolon, slash slash get the value indicated by pointer b and then post dash, increment b. 0, 2 of 0, 4, asterisk plus plus b, semicolon, slash slash increment pointer b and then get a new value to which it points. 0, 3 of 0, 4, plus plus, asterisk, b, semicolon, slash slash increment the value indicated by the pointer b. 0, 4 of 0, 4, open parenthesis, asterisk, b, close parenthesis, plus plus, semicolon, slash slash increment the value indicated by the pointer b. A typical comma, but rather complex statement involving these operators is colon. Asterisk, b plus plus equals asterisk, q plus plus, semicolon. In this case, comma, in which both pointers are post dash, incremented, comma, the value indicated by q is copied to the value indicated by p, comma, then p is incremented, comma, and then q is incremented. It would be roughly equivalent to these three statements, colon. Line 0, 1 of 0, 3, asterisk, b equals asterisk, q, semicolon. Line 0, 2 of 0, 3, plus plus b, semicolon. Line 0, 3 of 0, 3, plus plus q, semicolon. Like always, comma, parentheses reduce confusion by adding legibility to expressions. Pointers and const. Pointers can be used to access a variable by its address, comma, and this access may include modifying the referenced value. But it is also possible to declare pointers that can access, comma, but never modify, comma, the data to which they point. For this, comma, we use the keyword double quote, const double quote. In the following 5-line example, comma, we declare two integer variables named double quote, x double quote, and double quote, y double quote. In this case, comma, let's assume that we want to initialize y with a value of 10, comma, and we want to double quote, protect double quote, that value so that it won't ever be changed. We will create a new pointer named double quote, p double quote, that we will initialize to point to y, comma, and we will declare that it is a const pointer, meaning that the value to which it points should never be changed. Then we will use p to copy the contents of y into x. Finally, comma, we will illustrate an error by reversing that copy operation. Here are the 5 lines of code, colon. Line 0, 1 of 0, 5, int x, semicolon. Line 0, 2 of 0, 5, int y equals 10, semicolon. Line 0, 3 of 0, 5, constant asterisk, b equals ampersand, y, semicolon. Line 0, 4 of 0, 5, x equals asterisk, b, semicolon, slash slash ok colon reading b. Line 0, 5 of 0, 5, asterisk, b equals x, semicolon, slash slash error colon modifying p, comma, which is const dash, qualified. Here, comma, pointer double quote, p double quote, points to a variable, but points to it in a const dash qualified manner, meaning that it can read the value pointed, but it cannot modify it. Note that in the initialization of our pointer p, the expression ampersand y will be interpreted as a pointer to an integer, open parenthesis, because the previous line declared y to be an integer, close parenthesis, but that expression is then assigned to a pointer of type constant. This is allowed: a pointer to non-const can be implicitly converted to a pointer to const, but not the other way around. As a safety feature, pointers to const are not implicitly convertible to pointers to non-const. Sometimes it is handy to use const pointers to pass protected parameters into a function. Consider this example. In 31 lines: it creates two new functions, named increment underscore all and print underscore all respectively, and it makes extensive use of pointers. The main function initializes a small array of integers to the values 10 20 and 30 and then invokes the increment underscore all function to increment all three digits. Then it calls print underscore all to display the results. As you might expect, we never want our print underscore all function to modify any of the data that we pass into it, so we declare all of the pointers it receives, and the pointers it uses internally, to be of type const. Here is the 31 line example program: line 0, 1 of 31 / pointers as arguments, line 0, 2 of 31, $, include left angle bracket, IOStream right angle bracket. Line 0, 3 of 31, using namespace std, line 0, 4 of 31. Line 0, 5 of 31, void increment underscore all, open parenthesis, ind asterisk, start, ind asterisk, stop, close parenthesis. Line 0, 6 of 31, open curly brace. Line 0, 7 of 31, ind asterisk, current equals start, Line 0, 8 of 31, while, open parenthesis, current exclamation, equals stop, close parenthesis. Line 0, 9 of 31, open curly brace. Line 10 of 31, open parenthesis, asterisk, current, close parenthesis, / increment value referenced by current pointer. Line 11 of 31, current, / increment pointer. Line 12 of 31, close curly brace. Line 13 of 31, close curly brace. Line 14 of 31. Line 15 of 31, void print underscore all, open parenthesis, constant asterisk, start, constant asterisk, stop, close parenthesis. Line 16 of 31, open curly brace. Line 17 of 31, constant asterisk, current equals start, Line 18 of 31, while, open parenthesis, current exclamation, equals stop, close parenthesis. Line 19 of 31, open curly brace. Line 20 of 31, see out, double left arrow, asterisk, current, double left arrow, single quote, new line, single quote, / display value reference by current pointer. Line 21 of 31, current, / increment pointer. Line 22 of 31, close curly brace. Line 23 of 31, close curly brace. Line 24 of 31. Line 25 of 31, int main, open parenthesis, close parenthesis. Line 26 of 31, open curly brace. Line 27 of 31, int numbers left square bracket right square bracket equals, open curly brace 10, 20, 30, close curly brace, Line 28 of 31, increment underscore all, open parenthesis, numbers, numbers plus 3, close parenthesis, Line 29 of 31, print underscore all, open parenthesis, numbers, numbers plus 3, close parenthesis, Line 30 of 31, return 0, Line 31 of 31, close curly brace. Running that program generated the following output: 11, 21, 31. Note that print underscore all uses pointers that point to constant elements. These pointers point to constant content they cannot modify, but they are not constant themselves, that is, the pointers can still be incremented or assigned different addresses, although they cannot modify the content they point to. Constant pointers can have a second constant dimension too. Sometimes you may see the keyword double quote, const double quote, twice within a single expression, such as when the declaration of one constant pointer follows the usual asterisk with a pointer to another constant value. Consider these 5 statements, each followed by an explanatory comment, keeping in mind that the syntax with constant pointers is tricky and sometimes seems double quote, backward double quote, to beginners, Line 0, 1 of 0, 5 index, semicolon, / regular integer x. Line 0, 2 of 0, 5 int asterisk, p1 equals ampersand, x, semicolon, / regular pointer p1 gets the address of x. Line 0, 3 of 0, 5 constant asterisk, p2 equals ampersand, x, semicolon, / regular pointer p2 gets the const address of x. Line 0, 4 of 0, 5 int asterisk, const p3 equals ampersand, x, semicolon, / const pointer p3 gets the address of x. Line 0, 5 of 0, 5 constant asterisk, const p4 equals ampersand, x, semicolon, / const pointer p4 gets the const address of x. The syntax with constant pointers is definitely tricky. At first exposure, some of the syntax seems to be backward, and recognizing the cases that best suit each use tends to require some experience. In any case, it is important to get this concept of using constants with pointers, open parenthesis, and references, closed parenthesis, right sooner rather than later, but you should not worry too much about grasping everything, if this is the first time you are exposed to the mix of constant pointers. More use cases will show up in coming chapters. To add a little bit more confusion to the syntax of const with pointers, the const qualifier can either precede or follow the pointed type, with the exact same meaning, as shown in these 2 statements, Line 0, 1 of 0, 2 constant asterisk, p2a equals ampersand, x, semicolon, / declares a regular pointer named double quote, p2a double quote, as constant. Line 0, 2 of 0, 2 int const asterisk, p2b equals ampersand, x, semicolon, / also declares regular pointer double quote, p2b double quote, as constant. As with the spaces surrounding the asterisk, the order of const in this case is simply a matter of style. This chapter uses a prefix const, as for historical reasons this seems to be more extended, but both are exactly equivalent. The merits of each style are still intensely debated on the internet. Pointers and string literals. As discussed earlier, string literals are arrays containing null dash, terminated character sequences. In earlier examples, string literals have been directly inserted into cout, and also to initialize strings, and to initialize arrays of characters. But string literals can also be accessed directly. String literals are arrays of an appropriate type for the character set in use, containing all of the designated characters constituting the text of the string, plus the terminating null dash, character. Each of the elements of this string literal are interpreted as being of type const char, open parenthesis, as literals, they can never be modified, closed parenthesis. For example, const char asterisk, foo, equals double quote, hello double quote, semicolon. This declares an array with the literal representation for double quote, hello double quote, and then a pointer to its first element is assigned to double quote, foo, double quote. If we imagine that double quote, hello double quote, is stored at the memory locations that start at address 1702, we can represent the associated memory as the following addresses: 1702 equals H, 1703 equals E, 1704 equals L, 1705 equals L, 1706 equals O, 1707 equals 0. Of course, a pointer named double quote, foo, is also located somewhere in memory, and its value is 1702. Note that here double quote, foo, double quote, is a pointer and contains the value 1702, and not single quote, H, single quote, nor double quote, hello double quote, although 1702 indeed is the address of both of these. The pointer double quote, foo, double quote, points to a sequence of characters, and because pointers and arrays behave essentially in the same way in expressions, foo, can be used to access the associated characters by treating it either as a pointer or as an array. For example, consider these 2 lines: line 0, 1 of 0, 5 asterisk, open parenthesis, foo plus 4, closed parenthesis. line 0, 2 of 0, 5 2, left square bracket 4 right square bracket. Both expressions have a value of, single quote, O, single quote, open parenthesis, the fifth element of the array, close parenthesis. Pointers to pointers. C++ allows the use of pointers that point to pointers. These, in turn, point to data, open parenthesis, or even to other pointers, close parenthesis. The syntax simply requires an asterisk for each level of indirection in the declaration of the pointer. Consider these 6 statements: line 0, 1 of 0, 6 char A, line 0, 2 of 0, 6 char asterisk A, semicolon, line 0, 3 of 0, 6 char asterisk C, semicolon, line 0, 4 of 0, 6 A equals, single quote, C, single quote, semicolon, line 0, 5 of 0, 6 B equals ampersand, semicolon, line 0, 6 of 0, 6 C equals ampersand, A, semicolon. Thus, assuming the randomly chosen memory locations for each variable of 7,230, 8,092, and 10,500 to, the names and contents of those memory cells could be represented as : address 7,230 equals Z, single quote, open parenthesis, variable double quote, a double quote, close parenthesis, address 8,092 equals 7,230, open parenthesis, variable double quote, B double quote, close parenthesis, address 10,502 equals 8,092, open parenthesis, variable double quote, C double quote, close parenthesis. A new thing in this example is variable C, which is a pointer to a pointer, and can be used in 3 different levels of indirection, each one of them would correspond to a different value. Consider these 3 examples: example 1 of 3, double quote, C double quote, is of type char asterisk, open parenthesis, a pointer to a pointer, close parenthesis, and has a value of 8,092, because it points to pointer double quote, B double quote. The declaration of double quote, C double quote, is double quote, char asterisk, C, semicolon. Read this as double quote, C is a pointer to a character, double quote. Example 2 of 3, double quote, asterisk, C double quote, is of type char asterisk, open parenthesis, a pointer to a char, close parenthesis, and has a value of 7,230. Read double quote, asterisk, C double quote, as double quote, C points to a pointer with this value double quote. Example 3 of 3, double quote, asterisk, C double quote, is of type char and has a value of, single quote, C, single quote. Read double quote, asterisk, C double quote, as double quote, C points to a pointer which points to this value, double quote. Void pointers. The double quote, void double quote, pointer is a special type of pointer. In C++, void represents the absence of type. Therefore, void pointers are pointers that point to a value that has no type, open parenthesis, and thus also an undetermined length and undetermined dereferencing properties, close parenthesis. This gives void pointers a great flexibility. They are able to point to any data type, from an integer value or a float to a string of characters. In exchange, they have a great limitation: the data to which they point cannot be directly dereferenced, open parenthesis, which is logical, since we do not know the size or type of data being referenced, close parenthesis, and for that reason, any address contained within a void pointer must first be transformed into some defined pointer type, before its data can be referenced. One of its possible uses may be to pass generic parameters to a function, as shown in this 29-line example, which creates a new function named double quote, increase double quote, which expects a pointer to something, as input. Because the pointer could point to any of several different kinds of data, it is designated to be of type double quote, void double quote, and another input parameter, which it will name double quote, psize double quote, and designating the size of the associated variable, is also expected. The function then examines the value of double quote, psize double quote, to determine whether the associated pointer should be treated as a pointer to characters or as a pointer to integers. Once that determination is made, double quote, increase double quote, can take whatever steps may be necessary to create new pointers of an appropriate type, through which it can increment the referenced value. Down toward the bottom of this little program, our double quote, main double quote, function creates a character variable named double quote, a double quote, and an integer variable named double quote, b double quote. Each of these is initialized to a value chosen for purposes of illustration in this example, and then a pointer to each is passed to the new increase function, along with an indication of the size of the associated variable. Finally, the two ultimate values are displayed to the user. Here are the 29 lines of code implementing all of this: line 0, 1 of 29 / increaser. Line 02 of 29, $, include left angle bracket, IOStream right angle bracket. Line 03 of 29, using namespace std, Line 04 of 29. Line 05 of 29, void increase, open parenthesis, void asterisk, data, in p size, close parenthesis. Line 06 of 29, open curly brace. Line 07 of 29, if, open parenthesis, p size equals size of, open parenthesis, char, close parenthesis, close parenthesis. Line 08 of 29, open curly brace / get here, if data can be treated as a char. Line 09 of 29, char asterisk, p char, semicolon / create a new char pointer named p char . Line 10 of 29, p char equals, open parenthesis, char asterisk, close parenthesis, data, semicolon / point p char at data and cast data as a character pointer. Line 11 of 29 open parenthesis, asterisk, p char, close parenthesis, semicolon / increment the referenced data. Line 12 of 29, close curly brace. Line 13 of 29, else, if, open parenthesis, p size equals size of, open parenthesis, int, close parenthesis, close parenthesis. Line 14 of 29, open curly brace / get here, if data can be treated as an int. Line 15 of 29, int asterisk, pt int, semicolon / create a new integer pointer named pt int . Line 16 of 29, pt int equals, open parenthesis, int asterisk, close parenthesis, data, semicolon / point pt int data and cast data as an integer pointer. Line 17 of 29 open parenthesis, asterisk, pt int, close parenthesis, semicolon / increment the referenced data. Line 18 of 29, close curly brace. Line 19 of 29, close curly brace / end of function increase . Line 20 of 29. Line 21 of 29, int main, open parenthesis, close parenthesis. Line 22 of 29, open curly brace. Line 23 of 29, char equals, x, semicolon. Line 24 of 29, int b equals 1602, semicolon. Line 25 of 29, increase, open parenthesis, ampersand, a comma, size of, parenthesis, a. Line 26 of 29, increase, open parenthesis, ampersand, b comma, size of, open parenthesis, a, close parenthesis, semicolon. Line 27 of 29, see out, double left arrow, a, double left arrow, double quote, comma, double left arrow, a, double left arrow, new line, semicolon. Line 28 of 29, return 0, semicolon. Line 29 of 29, close curly brace. Running this program generated the following output: y, 1603. As you can see, x became y and 1602 became 1603. Each of those two variables, of different types, was increased by the single new function named increase, which knows how to accept a void pointer with its associated data length. You probably noticed that the previous example made use of a function named size of . This is integrated in the C++ language, and for any computing environment, it returns the actual size in bytes of its argument. For non-dynamic data types, this value is a constant. Therefore, for example, size of, open parenthesis, char, close parenthesis, is 1, because char is always has the size of 1 byte. Invalid pointers and null pointers. In principle, pointers are meant to point to valid addresses, such as the address of a variable or the address of an element in an array. But pointers can actually point to any address, including addresses that do not refer to any valid element. Typical examples of this are initialized pointers and pointers to non-existent elements of an array. Consider the following 3-line code snippet: line 01 of 03 int asterisk b semicolon / an initialized pointer, open parenthesis, local variable, close parenthesis. Line 02 of 03 int my array left square bracket and right square bracket, semicolon. Line 03 of 03 int asterisk q equals my array plus 20, semicolon / element out of bounds. Neither p nor q point to address is known to contain a value, but none of the above statements causes an error. In C++, pointers are allowed to take any address value, no matter whether there actually is a defined entity at that address or not. What can cause an error is to dereference such a pointer, open parenthesis, that is, actually accessing the value to which they point, close parenthesis. Accessing such a pointer causes undefined behavior, ranging from an error during runtime to accessing some random value. But sometimes, a pointer really needs to explicitly point to nowhere, and not just an invalid address. For such cases, C and C++ define a special value that any pointer type can take: the double quote, null pointer double quote, value. This value can be expressed in C++ in two ways: either with an integer value of 0, or with an LPTR keyword, as shown in the following two statements: line 01 of 02 int asterisk b equals 0, semicolon. Line 02 of 02 int asterisk q equals null ptr, semicolon. Here, both b and q are null pointers, meaning that they explicitly point to nowhere, and if they were to be tested for equality, they both actually compare as equal. All null pointers compare equal to all other null pointers. It is also quite usual to see the defined constant double quote, null double quote, used in older code to refer to the null pointer value: int asterisk r equals null, semicolon. Null is defined in several headers of the standard library, and is defined as a name for some null pointer constant value, open parenthesis, such as 0 or null ptr, close parenthesis. Do not confuse null pointers with void pointers. A null pointer is a value that any pointer can take to represent that it is pointing to double quote, nowhere double quote, while a void pointer is a type of pointer that can point to somewhere without a specific type. The first, open parenthesis, void, close parenthesis, refers to the value of a known type stored at the referenced memory location, and the other, open parenthesis, null, close parenthesis, refers to the type of data to which it points, open parenthesis, in this case none, close parenthesis. Pointers to functions. C++ allows operations with pointers to functions. The typical use of this is for passing a function as an argument to another function. Pointers to functions are declared with the same syntax as a regular function declaration, except that the name of the function is enclosed between parentheses and an asterisk is inserted before the name, as shown in the following 27-line program, which creates three new functions named double quote, addition double quote, subtraction double quote, and double quote, operation double quote. The first two functions each expect upper integers, and they both perform a simple mathematical operation on them and return the result. The third new function, open parenthesis, named double quote, operation double quote, close parenthesis, also accepts two integers, but it also expects a pointer to one of the other new functions, so that it can either add them, or subtract them. Down toward the bottom of this example, the double quote, main double quote, function exercises all of the other functions with some sample integers chosen for illustration. The 27 lines of source code for all of this are: line 01 of 27 / pointer to functions. Line 02 of 27, $, include left angle bracket, iostream right angle bracket. Line 03 of 27, using namespace std, semicolon. Line 04 of 27. Line 05 of 27, in addition, open parenthesis, int x, int y, close parenthesis. Line 06 of 27, open curly brace, return, open parenthesis, x plus y, close parenthesis, semicolon, close curly brace. Line 07 of 27. Line 08 of 27, in subtraction, open parenthesis, int x, int y, close parenthesis. Line 09 of 27, open curly brace, return, open parenthesis, x dash, y, close parenthesis, semicolon, close curly brace. Line 10 of 27. Line 11 of 27, in operation, open parenthesis, int, open parenthesis, asterisk, functical, close parenthesis, open parenthesis, int, close parenthesis. Line 12 of 27, open curly brace. Line 13 of 27, int g, semicolon. Line 14 of 27, g equals, open parenthesis, asterisk, functical, close parenthesis, open parenthesis, n, close parenthesis, semicolon. Line 15 of 27, return, open parenthesis, g, close parenthesis, semicolon. Line 16 of 27, close curly brace. Line 17 of 27. Line 18 of 27, int main, open parenthesis, close parenthesis. Line 19 of 27, open curly brace. Line 20 of 27, int t, u, semicolon. Line 21 of 27, int, open parenthesis, asterisk, minus, close parenthesis, open parenthesis, int, close parenthesis, equals subtraction, semicolon. Line 22 of 27. Line 23 of 27, t equals operation, open parenthesis, 7, 5, addition, close parenthesis, semicolon. Line 24 of 27, u equals operation, open parenthesis, 20, n, minus, close parenthesis, semicolon. Line 25 of 27, see out, double left arrow, u, semicolon. Line 26 of 27, return 0, semicolon. Line 27 of 27, close curly brace. Running this program resulted in the following output: 8. In the example above, double quote, minus double quote, is a pointer to a function that expects two integer parameters as inputs, and which returns an integer. It is directly initialized to point to the function double quote, subtraction double quote. Here is the syntactically complex line that performs that initialization: int, open parenthesis, asterisk, minus, close parenthesis, open parenthesis, int, close parenthesis, equals subtraction, semicolon. Within the double quote, main double quote, function, the code invokes a new double quote, addition double quote, function by specifying double quote, addition double quote, as an argument to double quote, operation double quote, which then invokes a new double quote, addition double quote, function and adds the associated input parameters. Double quote, main double quote, also invokes the double quote, new double quote, subtraction double quote, function, but for purposes of illustration, it does so through an additional level of indirection through the new pointer named double quote, minus double quote. Note the declaration for the new double quote, operation double quote, function. It is rather complicated and it reads like this: in operation, open parenthesis, int, open parenthesis, asterisk, functical, close parenthesis, open parenthesis, int, close parenthesis. This means that our new function named double quote, operation double quote, expects three input parameters, but the third parameter is syntactically complex, following the same complex pattern that we showed in our description of the new pointer that we named double quote, minus double quote. The three arguments to double quote, operation double quote, are: 1 of 3, an integer to be named double quote, and double quote, within the function. 2 of 3, an integer to be named double quote, and double quote, within the function. 3 of 3, a pointer to another function returning an integer, which in turn expects another pair of integers. That third parameter actually consists of several parts, but it is necessary in order to provide enough information to satisfy the needs of the additional function that is referenced. Don't worry too much if the syntax used in the declaration of a function that expects a pointer to another function as an input parameter seems hard to understand. With a little thought you will come to appreciate how powerful this concept is and that all of that information is really necessary in order for one function to know how to invoke another function.